Okay, welcome back everyone. We were talking about Q-series identities, not partition identities, Q-series identities, and Ali and Joanne gave you partition interpretations of Q-series identities. I will continue the same stuff today. I promised to rewrite all three iterations of Heine's transformation, but because of time limitations, I decided to give you only two corollaries of the first iterative. So let me rewrite Heine's transformation again. And at many points, we'll make references to the Q Binomial Theorem. I'll write that down when the time comes. Heine's transformation with this Q Pockhammer symbols is the sum n running from 0 to infinity, two parameters on top, two parameters down below, a, b, base q sub n. And one of the bottom parameters must always be q. The argument is z to n. This equals an infinite product quotient of four infinite products, and then a similar sum. And those infinite products have parameters. Where are they? B, A, Z, Q sub infinity, C and Z, Q sub infinity, and then another 2 phi 1 sum. Where the top parameters are C over B and Z, the argument becomes B, and then the bottom parameters, one of them is Q, the other one is A times Z. We'll see two spatializations first. Let's see if I can pull this off. So you want to replace Z by something else. In particular, we want to replace Z by C divided by A times B. Yes. Such series have a spatial name. I'll tell you that name in a second. When we do that, well, not much happens on the left. N equals 0 to infinity. A, B, just copy these. But lots of things happen on the right. First, what becomes of A times Z? Well, Z is C divided by AB, so A times Z is going to be C divided by B. And downstairs we have C and C divided by AB. If you saw this before, you see where I'm going with it. Make the same substitutions here as well. C divided by B, C divided by AB. These finite products. Q and A times Z, what was it? C divided by B. B to N. And then there is a simplification inside the sum, C divided by B, Q sub infinity, Q sub N, I'm sorry. They go away, and we are left with one parameter on top, no parameters other than Q. This calls for an application of the Q Binomial Theorem. Let's write it here. The Q Binomial Theorem n running from 0 to infinity, a sub n divided by. Let's not forget the base because we'll be playing with the base in a minute too. Z to n. This is a quotient of two infinite products. A times z divided by z q sub infinity. Yes?
In the last line there, we forgot the power of z, I think, on the left-hand side. When we said...
Oh, yes, you're right, yeah. Thank you. So we have c divided by a times b altogether raised to n. Thank you, Halime. Any other questions, corrections? Okay. Now, here, c divided by ab will play the role of a. Yes, b will play the role of z. Altogether, this Q hypergeometric sum can be written as a quotient of two infinite products, and they are going to be a times z is, what is it? C over ab times b, c divided by a, q sub infinity, divided by the argument, q sub infinity. If they combine with the infinite products up front, there are further simplifications. No, only one simplification. These b's go away. And we obtain the theorem called Q Gauss. That's called the Q Gauss summation formula. If you want this series to converge, you require c divided by ab less than 1 in modulus, but I'm not going to write that down. It says from n equals 0 to infinity, ab q sub n divided by q c q sub n, c divided by ab equals quotient of two infinite products, which are c over a, c over b, c over a times b. And like Ali mentioned yesterday, this has a nice combinatorial proof, which I will not go into. In fact, if I'm not mistaken, there are at least two combinatorial proofs of these. Anyway, this is the Q Gauss summation. One corollary of Heine's transformation. Heine's transformation, first iterate. Any questions, comments? Okay. For the second one, I will replace z by something else. This is specialization number 2. Let's replace z by z divided by a times b. And then, what am I going to do? I will send set c equal to z as well. And then I will send a and b to 0. Yes. I want to double check before going into details. A and b to 0. Yes. Yes, no? Infinity. Probably infinity, yes. Well, let's make the substitution first and then let's see where we're going with that. Okay, take the identity, make the replacements, and from 0 to infinity, a and b stay. Z is replaced by this thing, a to n, b to n, over, yes, we are sending them to infinity. Q and Z. What do we have on the right? We have B. A times Z will become Z divided by B. Over C and Z divided by A. I'm not sure what's going to happen with this B here, but we will see. We will see. And inside, from n equals 0 to infinity, C divided by B will become, what is it? Z divided by B. Z divided by A times B, Q sub n, Q, and A times Z is, what is it going to be? Z divided by B. Oh, I think we can do this. We can do this, yes. So before taking the limit, perform the simplification, apply the Q binomial theorem, so this one goes away, and then we can take the limit. Yes, yes. So there's an intermediate step here. Apply the Q binomial theorem. Cancel these, and like we did before, write this as a quotient of two infinite products. This times that Z divided by A, Q sub infinity, divided by, what is it? B, Q, infinity. And then there's one more cancellation. Write that formula, and we are good. We are good. Let's rewrite just the far left and the far right. Let me write these separately because we are going to combine this with the first batch of factors, this one with the second batch of factors. We are going to leave Z to n alone. And downstairs we have Q, Z, Q sub infinity equals something very similar to Gauss's theorem. Yeah, we could have used Gauss's transformation. Oh well. Okay, now we can take the limit, take A and B to infinity. This, and that, they are going to go to 0. Which means that the corresponding infinite products will become 1s. Corresponding infinite products will become 1, and the only survivor is 1 over Z Q sub infinity. On the left, what's happening? Well, let's color code things. A Q sub n and 1 over n. This is 1 minus A, 1 minus AQ, up to 1 minus AQ to n minus 1. We distribute one factor into each of these parentheses divided by A, all the way to the end. And the parentheses become what? 1 over a minus 1, 1 over a minus q. I think we did this yesterday again. Q to n minus 1. Send a to send a to infinity so that all of these guys become zeros. So we have minus 1 to n, q to n choose 2. That's one contribution. Something similar happens for the second parenthesis. Coming from the second batch. Minus 1 to n, q to n minus 2, n choose 2. Minus 1 to n, minus 1 to n, when multiplied, they give us plus 1. And n choose 2, 2 of them together will give us q to n squared minus n. And we have a new identity. This identity is a named identity as well. But I don't remember the name. Do you? Therefore, we have n running from 0 to infinity, q to n squared minus n, z to n, divided by q, z, q sub n equals 1 over z, q sub n. If you plug in z, yes? Oh yes, infinity, you're right. If you plug in z equals q, this is the partition function. This generates all partitions. Therefore, the left-hand side must generate all partitions as well. But I'm not giving you the combinatorial explanation at this moment. Maybe if we have time later, I'll give you, or if Ali wants to do it, I'll leave it to him. There's also a nice combinatorial proof, and the combinatorial proof is much less boring than this one. Okay, these were the two significant corollaries of Heine's transformation, but in the literature there are lots and lots of applications of Heine's transformation. Take various limits, make various substitutions, substitute, reduce, do that in some order, do that repeatedly, so on and so forth. In other words, Heine's transformation is a very versatile trick. I promised you one more thing. I promised to tell you what type of series this is called. You multiply the top parameters. You multiply the bottom parameters except for q, the top parameters and the argument. You multiply the bottom parameters except for q, and if they equal each other, a times b times c divided by ab, is that equal to c? Believe me, it is. Such hypergeometric series are called balanced. Such Q hypergeometric series are called balanced. And we like balanced series better than others because they yield to nicer formulas. If we have a balanced series, we can expect for an infinite product. If we don't have a balanced series in the general case, it's impossible to write Heine's transformation as an infinite product. So we must have a sum somewhere. We must have a series somewhere. But once we have a balanced condition, once we have the balanced condition, then we have an infinite product. I will proceed with Jacobi's triple product identity if you don't have any questions. Okay. So, until yesterday, I was planning to use this last corollary as a starting point of Jacobi's triple product identity, but then I remembered that in Bruce Bourne's book, number theory in the spirit of Ramanujan, there is a proof attributed to Andrews and one other mathematician which relies on Q binomial theorem alone. So here's my suggestion of reading for you. Number theory in the spirit of Ramanujan. I even had the Indian spatial edition, that spatial copy, but somebody ran away with it. I won't name the guy, but if I see him, I'll ask it back. So, okay, I'm not going to keep Heine's transformation on the board. Okay, let's try to reproduce the theorem. I will not state the theorem. Let's do the manipulations and then write the result as Jacobi's triple product identity. Our goal, derive Jacobi's triple product identity. Hereafter will be named JTP. And this is one of the most powerful formulas in the theory, or depending on your point of view, this is one of the bottlenecks of the theory. Because one line of Roger Ramanujan generalizations, all of them depend on Jacobi's triple product identity. All of them. Anyway, now we will take the Q binomial theorem. This time we will replace the base with something else. So using the Q binomial theorem, let's expand 1 over z times q z times q squared infinity. Later we will reduce this q squared to q, but this is a little more convenient to do it this way. So using the Q binomial theorem, where A is 0, yes? A is 0, z is replaced by z times q, q is replaced by q squared. No, q is replaced by q squared first. After that, z is replaced by z times q, and a is replaced by 0. So the order in which you do the substitutions matter. Anyway, this is from n equals 0 to infinity. What is it? The top factor goes away, z to n, q to n, divided by q squared n. We will take this, make it an infinite product, factor it out, and we have to multiply by the missing factors as well. If you multiply and divide by the same thing to make this guy an infinite product, we are gonna get 1 over q squared infinity times from n equals 0 to infinity, z to n, q to n. What's going to be missing? Well, this starts at 1 minus q, 1 minus q squared, 1 minus q to 4, 1 minus q to 6, up to 1 minus q to 2n. The first missing factor is 1 minus q to 2n plus 2. And then we'll keep going with the base q squared. Now here's the first bunny out of the hat. If we consider negative n's, then the first factor is 1 minus q to 2m plus 2 is either 0 or negative. Yes? We start at the negative side, and then we keep hopping on the even numbers, minus 6, minus 4, minus 2, 0. And once you hit 0, it's 1 minus q to 0, which is 1. So this whole product becomes 0 if n is negative. So it's no harm to let the sum run from minus infinity to plus infinity, replacing a unilateral sum by a bilateral one. 1 over q squared infinity times from n equals 0 to infinity. No, I said n equals minus infinity to plus infinity. Z to n, q to n. And for that inside infinite product, we will use the Q binomial, not the Q binomial, a corollary of the Q binomial theorem. Let's remember, A, did we call it A? Whatever. A q sub infinity is A to n, q to n choose 2 divided by q sub n. Did I write it correctly? There's a negative power as well. I think we are good. Yes, yes. So use that corollary to replace that infinite product with an infinite sum, which runs from m equals 0 to infinity, but this time q is replaced by q squared, remember. So we will have minus 1 to m, q to n squared minus, m squared minus m, times the argument raised to m, q to 2mn plus 2m, all over q sub n. I think we're good. Any questions here? Now we will switch the order of summations, see if we can combine any of the, if we can replace the inner sum by an infinite product. Again, one of the tricks we employed yesterday. Switch the order of summation. Do we? Yes, we will switch the order of summation. We may need to do some shifting at some point, but we will see. From m equals 0 to infinity, minus 1 to m, q to m squared minus m, q to 2m. This has to stay inside the inner sum. It depends on both indices. Both indices. qm. And inside we have n running from minus infinity to plus infinity, z to n, q to n times q to 2 times m times n. I was expecting square powers inside the inner sum. we expected square indices, square exponents. I found my mistake. So here's the mistake. If you want quadratic powers here, then you need quadratic powers there. If you want quadratic powers here, then you need quadratic powers there. And in order to have quadratic powers there, we start with the wrong infinite product. Okay. Start over. I'm doing it in fast forward mode. Start over, use ZQ, Q squared sub infinity in the numerator, not in the denominator. Okay, this time we will have from n equals 0 to infinity, minus 1 to n, Q to n squared minus n. Yes, the quadratic powers will come from here, times the argument z to n, q to n, so you can forget about this minus n there, q squared sub n. Again, make this an infinite product, 1 over q squared sub infinity, and running from 0 to infinity, these guys, minus 1 to n, q to n squared, z to n times, what was it? Q to 2m plus 2, q squared sub infinity. Because this is going to be 0 for negative n's, replace this by, and from minus infinity to plus infinity, replace this by a similar sum using a second index. Now we are good. Okay. M running from 0 to infinity, minus 1 to m, q to m squared minus m, q to 2mn plus 2m over q squared sub m. Okay. I hope I didn't make any mistakes this time. Now switch the order of summation. The outer sum is a unilateral sum from m equals 0 to infinity this time, minus 1 to m, q to m squared minus m. What is it? We don't have any z's, do we? No. Q to 2m. But we will get more z's in a minute. And the inner sum is from n equals minus infinity to plus infinity, and we are getting our beloved quadratic exponents, minus 1 to n, q to, what is it, n squared plus 2mn What else? Did I miss anything? Did I forget anything?
Z to the n.
Oh, we have z to the n. What else? Okay. Now, if I take this m squared and write it here, we are going to get a perfect square, yes? So this is going to be n plus m in parentheses squared. Also, I can merge this minus 1 to m with that one and forget about the powers of minus 1s here. Finally, if only I could make this z to n plus m, then I can shift the index in the inner sum. I cannot do that. Why not? Because I don't have z to m. But if I write z to minus m here, I think we are good. Yes. Now in the innermost sum, shift the index replace n by n minus m. Nothing is going to happen because it's a bilateral sum running from minus infinity to plus infinity. It's still going to run from minus infinity to plus infinity. But all of these exponents, minus 1 to n plus 1 will become minus 1 to n, q to n squared here, and z to n. What's more, the first sum will be independent of n now. And we can use another binomial theorem for it. Did I forget something? Yes, I forgot something. We have this guy at the beginning. So this became 1 over q squared sub infinity times an independent sum, m running from 0 to infinity. What is it? Q to m, q divided by z raised to m, divided by q squared sub m, and a weird bilateral sum from n running from minus infinity to plus infinity, minus 1 to n, q to n squared, z to n. This is known as a theta function. Basically, if you have an arithmetic progression in the exponents, you have a geometric series. If you have a quadratic progression in the exponents, that's a theta function. Of course, you need to worry about convergence when you write a geometric series, because the series will converge if you go one way, but diverge if you go the other way. Remember Zof's talk in the morning, you have to go in a single direction. But when you have square powers, you can include both directions. Of course, there are deeper mathematical reasons of writing theta functions this way, but one way to remember theta functions is that when you have quadratic exponents instead of linear exponents. Anyway, that's our theta function. We'll leave it as it is, and for that one, we will apply the Q binomial theorem once more to see that this is nothing but 1 over Q divided by Z, Q sub infinity. So this is the far right. What's the far left? Far left was this thing. Far right is that thing. If we leave this theta function alone on one side, this is the Jacobi's triple product identity. So Jacobi's triple product identity is this theta function n running from minus infinity to plus infinity, minus 1 to n, Q to n squared, z to n, is a triple product. Q times z, Q divided by z, Q squared sub infinity. When you write Jacobi's triple product identity, always make sure that the product of these two guys equals the third one, and the third one must be equal to the base. Questions, comments? Okay. The cake is here. I'll show you just one application. And then we'll be set free. So, replace Q by Q to 2/3. So we will have Q cubed here, and Q to 2/3, no, 3/2. Times z, Q to 3/2 divided by z. Replace Q by Q to 3/2 and set z equal to, what is it, Q to 1/2. Once you set z equals Q to 1/2, this is going to be Q squared. This is going to be Q, and both Ali and Joanne showed you that if you have Q squared, and Q cubed sub infinity, this is going to be Q sub infinity. What happens on the left-hand side? So let's see. -1 to n stays. Q to n squared is going to be Q to 3/2 n squared. Z is going to be Q to n over 2. Am I right? I think I am. Okay. And if you write the two together, this is going to be from n equals -infinity to +infinity, -1 to n, Q to n times 3n plus 1 divided by 2. Ladies and gentlemen, this and that is Euler's Pentagonal number theorem. Once again, we arrived all this way doing college algebra. And if you do the bookkeeping correctly, well, okay, there were some arguments on the way, some intricacies like replacing the bottom end by n equals -infinity. But other than that, we are doing nothing but college algebra, and we can reach as far as Euler's Pentagonal number theorem. That's a significant result, and Jacobi's triple product identity is a significant result on its own. As I said, one of the bottlenecks of the theory. Anyway, let me stop here today. Tomorrow, we will continue with more applications of JTP.